Hello, this is Kaishavi and this is lab 4 of course EE542. The goal of the lab is to design custom, fast, reliable file transfer protocol. As we all know, while TCP is effective, reliable, and relatively robust on the internet, it doesn't always give us the best throughput under every circumstance. So here we'll design an IP-based file transfer utility. Our goal is to develop a file transfer program that uses custom protocols to perform better than any other traditional protocols. So our requirements are, we need to use IP. The file should be transferred reliability with zero packet loss, and we need to implement it in a command line interface such as SCP. So here the link speed of the sender and receiver must be 100 Mbps and the test file size must be at least 1 GB. We have implemented this protocol for two MTU sizes, 1500 which is Ethernet and 9001 which is jumbo frame size of AWS. So here is our approach. We designed this protocol using divide and conquer method. One GB file is divided into 8 parts, each of 128 MB. So these all files are sent simultaneously, so we'll get a parallelism. With that, we have also used threads. So here, data is transmitted only by one UDP socket. Let's go to the code and see the approach. This is the sender file for 1500 MTU. We have set payload to 1464 because other bytes are for the headers of IP and UDP. First, we created a structure for sending the datagram. In the datagram, we will send the sequence number, the data size, and the data. Here we can see, first we created a file pointer of the file which we need to send. Then we created a socket, UDP socket. We have used a UDP socket to send the data from client to server and get back the NAG from server to client. After creating the socket, I've also set the UDP send and receive buffer size. I have taken the size of the file and sent it to the server, so it can calculate how many datagrams will be received by the server. And then I created a thread to continuously checking for NACs came from the server. Here we can see for the check client, we are receiving the NACs from the server and we are retransmitting the datagrams which was dropped in the link. So after creating the thread, we are continuously sending our data in a while loop. Here we used mmap to open the file and read from it. The mmap returns a pointer which is mapping to the file which is now in the main memory. And after all the data is received by the server will send a negative value. So here we are sensing that negative value in the UDP socket, so we can get to know that all the packets are received and we can close our sockets. And one more thing, we are continuously writing we're continuously sending the data to the server until we are not getting that negative value. This is the code of the receiver. This is similar as sender. We have created a structure to store our datagram. It's the same structure as we used at the sender side. Then here I have created a file in which I'll store the data came from the client. Then I created a socket, I bind it, and I set the send and receive buffer size at the UDP socket. Then I received the files I sent from the client, and then I calculated the number of datagrams that server will be receiving. I created a thread to check which sequence are missed or which sequence are dropped in the link and server didn't get it. So in this function, the check server, we are continuously checking the unavailable datagram which is tracked by one data structure and we are sending neg for the sequences missed. Find unavailable datagram function finds the datagram which are missed using a received datagram structure which keeps track of the missed datagrams. Now, after creating this thread, the server is receiving the file using receive from function at the UDP socket, and then it is checking if this segment is already received, then it will do nothing. If it is a new segment, then it will store it into the file. And if all segments are received, then it will send the negative value. So client will get to know that server has received all the packets and the both of server and client can close their socket. Here is the script which we run to divide 1 GB file into 8 files and process it simultaneously. So we are taking the file name and MTU from the user, and the seconds will keep track of the time to send the file from client to server. We have calculated the checksum to find the reliability of our protocol. So if the checksum at the client and the server will match, we will get to know that the file is transmitted reliably. So here we are splitting 1 GB file into 128 MB files using this command. We are compiling the protocol. If the M2U is 1500, we'll compile the respective code, otherwise we'll compile the other code. These are 8 processes running simultaneously for all 8 files, and at the last we are waiting for all the processes to be finished. After all the processes is finished and file is transferred successfully, we'll calculate the duration of the transmission, and then we'll calculate the throughput using that time, and then we'll print out all those information on the console. At the server side, it is similar. We'll write the size of MTU, and here are 8 processes which are run simultaneously. We are waiting for those processes to end, and then after when we get all the 8 files, we'll merge those files into one 1 GB file, and then we'll calculate the time to receive this file and throughput, and we'll calculate the checksum of the final data.bin file, and we'll check the both checksum at client and server to confirm that the file is transmitted fast and reliably.
Hi, I'm Aditya, and I'll be explaining the cases for this particular lab assignment, which is file transfer protocol fast and reliably. Right now, the case one talks about performing a protocol, file transfer protocol from client to server, and this is our router, using this particular network settings. So as you can notice, I have set my my ETH1 interfaces of client and server form the internal network, and it is connected via this router. So routers, both of the interfaces are part of the internal network, right? So we have set 100 megabits per second rate in our client as well as server, with the burst parameter as 9012, same as in server, and the latency is for how long the packets stay in the bucket. So that is also 1 microsecond in both client and server. So this is constant for all the 3 cases that I'll be talking about. The only changes that I'll be making for the cases is in the router. Now you can see that I have, for the case 1, I have set 100 megabits per second speed, burst, and the latency same as client and server on both of the interfaces, on ETH0 and ETH1. But for case 1, we need to have a delay of 5 milliseconds on each of the interfaces, because we need an RTT of 10 milliseconds as part of our case 1, and the loss should be 1% throughout the network. So that's why we are creating loss in the client router link and the router server link, right? So before I run my protocol, I just want to show what all do I have in my directory. So as you can see, data.bin is the 1 GB file that I want to send. So just to make sure that that's the thing. Oops, sorry. Yeah, so as you can see, this is 1 GB, and that's data.bin, and I'll be sending this file across to the server's end, right, using the via this router. So to run it, I'll first hit the bash command. Just before I do that, I just want to show that first I'll be running for the case MTU 1500. So this signifies how much maximum transmission that number of bytes that I could transmit in one particular go. So this is set on ETH1 interfaces, which is currently 1500. That's the same for client as well. So this is the client, the server. You can see the same for router as well, 1500 and 1500, right? Yeah, so now we run the script. So FRFTP stands for Fast Reliable File Transfer Protocol. And we'll do the same here. So first we enter the file name, data.bin, What have we set as the CPU size? This is the CPU size. We do the same on the server side. And as you can see, the 1 GB file is being split into 8 smaller files to be exact, so that 1 GB gets converted into 128 MB file. So 8 128 MB files. So what we are doing is we are using a divide and conquer approach. So we divide the 1 GB file and send that 8 128 MB files independently. So we have 8 programs running, and each program is using pthreads. So we are using an additional thread. So essentially we have 8 processes, independent processes, each process running 2 threads, right? So this is based on the algorithmic idea of divide and conquer strategy. So first we divide the load, and then we conquer what we needed to do. So we transfer independently, and then we merge it at the end. Okay, so as you can see that the client has already finished sending the file, and right now the server is merging. And as you can see, the throughput, so we essentially take the throughput from the server side because that's where we need our file. So as you can see, it took us 2 minutes and 4 seconds for the transfer to happen, and the throughput is 66 megabits per second. So how do we know it's reliable? We do a checksum, and as you can see, the checksum 128-bit checksum value matches completely. So this ensures that the transfer is complete. So we did this case one on an MTU 1500 interface. So now we talk about case 2, which is essentially the same the client and the server, but in the router we changed the delay and the loss. So now the RTT is supposed to be 200 milliseconds. That means we set 100 milliseconds in each 0 and 100 milliseconds in each 1 interface, and the loss throughout the network should be at least 20%, right? So our settings are always set, and we do the same thing again. We check what all files we have. So this is our file that's supposed to be sent it across, right? Let's start a script. For FTP client, here's the file name, and for now we are sticking with 1500 MTU interface, and we do the same on the server side as well. So same thing, the file is being divided into 8 separate files, and we send those files independently and then merge at the server side. And after we merge, that's when we stop our timer, right? So as you can see, this is the 128 byte, and on the server side it calculates how many datagrams that it corresponds to, depending upon our buffer size. So our buffer size is set with respect to our MTU and the custom packet header that we're using. So that's how we calculate the total datagrams needed to transfer a file size of, say, this. So it's pretty dynamic. So if you want to send straight away, you can send a 1 GB file, but we thought it's better that we divide and then send smaller files and then merge at the end. That was proving to be more quicker. Yeah. So as you can see here, we have received the file, and you can see the checksum are matching, and this is over the 20% packet loss link with a 200 millisecond RTT link, and the link speed is 100 megabits per second throughout. So you can see that the throughput is much less than what we received in the previous case one. We received around 66, if I'm not wrong. So 66 and 73 on this end. Now it's 43 and 40. So just to see whether we have actually got, yeah, so this is our 1 gigabit, and do this here also, you can see that it's 1 gigabit, and even the checksum is matching, right? Now we talk about case 3. So case 3 has the link speed set to 80 megabits per second with an RTT of 200 millisecond. And how we do that? We set 80 megabits on the router EE0 and EE1 interface, and delay of 1 millisecond in EE0 and EE1 interface. We keep the same setting in the client and the server. And yeah, so clear the screen, and for these cases, we are doing this for the MTU 1500. So we set MT 1500, we set it here as well, and then we wait. Yeah, so as you can see, the datagrams have been calculated on the server side, the file size has been calculated on the client side, and right now the transfer is happening as and when I'm speaking. Yeah, so as you can see, our receiver got the file and this is the checksum that's here, but if you notice, this client is still waiting for the ACK from the server. So this sometimes happen, and frankly we couldn't even investigate how this happens, but the file does transfer. So just to show that it does transfer, you can see that the checksum matches. So that's how you're able to conclude that even though this is not stopping, but we are getting the file transfer, so it does the job. And let's just show you that it's actually 1 GB. Yep, it is 1 GB. Yep. Now we come back to case 1, and now we do it for the MTU 9001 interface. So right now, if you can see, it's set to 1500. So what we do is change an EE1, MTU, and 1. Right? So if I do config again, it's done. So we do the same here as well. EE1, and same for both here. For EE0 as well. Okay, so when we do if config here, you see it's set, and this is what it sets, and this is what it's set. And I didn't show on the server side, and there we go. Right. So to ensure that we are using a 9001 jumbo frame, that's what the Amazon Web Services site says, that's what it's called, jumbo frame. So we can run the tracepath command to between hosts. So from the client, I'm sending trying to contact to my server using that, and it'll show you whether we are using the jumbo frame. So as you can see, it's 2 hops away because we have a router in between, and we are able to do it with 901. So just to check the other way around, 1.236. So these are the IP addresses of the EE1 interfaces of client and server. So this is for the server and this is for the client. I run that, and you get 2 hops. Now we run the script to check. So now this is data.bin, and we do the same on the other side. So now the size is 9001, so that's what we choose here. Put this here and put this here, and it follows the same step because we're just running the same script. And since I've chosen 9001, it'll compile the code which is pertaining to the 9001 jumbo frame. So right now it's at the stage where it's splitting, and as you can see, it completely split, and these are the total datagrams. So if you remember, it was around 9,000 when we used with 1500 MTU interface. It's now 26,000, which is in the previous year it was 90,000, not 9,000, my bad. So it's now 26,000. So there's a huge difference in the number of datagrams that are being sent due to this increased MTU interface. Yeah, so as you can see now, the throughput we are getting is 55 Mbps. So why are we getting less than what we got in the case 1? Because in case 1 we were getting when we were testing via iPerf, we got some 100 megabytes. That's what we are supposed to do. That's what the problem statement says, that we are supposed to get 100 megabytes when you run iPerf in TCP mode. But it came to me as a surprise when I do this on, now this is the case where I'm running MTU 9001, right? So when I do that, Yeah, that's the listing. So the first thing that I noticed is the window size has changed, right? Now the second thing, the previous case we had a link throughput of 100 megabytes, but now this link has a throughput of 12.4 megabytes. So considering that when we are testing via iPerf in TCP mode, the throughput is 12.4 megabytes. We are getting more than that. We are basically getting more than what TCP or any other file transfer protocol would be able to do in this particular link setting with this particular jumbo frame. And that's how I came to a conclusion that maybe, even though it's not more than what we had in 1500, because there in the link through we were getting some 100 megabytes throughput, for in that case we were getting 60 Mbps, which is less than what the link can offer. But now the link is offering us 12.4 megabytes with TCP, and our protocol exceeds that when we are using MTU 900. Okay, so now we test for case 2. So first we check whether we have the MTU 9001 interface set or not. As you can see, MTU 901, we do the same here. IP link show, EE542 is the interface that corresponds to our internal network. IP link show dev EE542. Right, so this is our basically the MTU network, for just to confirm that we are using in fact so this is the same command that I talked about minutes ago, that this shows, yeah, so this is 2 hops and we are able to send jumbo frames. So this confirms that basically, right? So now we set the setting for case 2. Queue disk show, oh yeah, queue disk show, yeah, so this is what we want here, but here we might have to change, yeah, so you have to change that to 20% and 100 milliseconds. That's what case 2 is, right? So instead of add, we do change. So we do change. Let's start with EE0. Our delay is supposed to be 100 and drop is supposed to be 20, and then we do the same thing for EE1. Same for EE1, and now we check whether the network is set. Yep, the network is set. We run the bash script for FTP server dash for FTP client data.bin. 901 is our MTU size, 901 MTU size. We do the same thing once again, right? Now here we expect more loss because it's 20% and increased delay, right? So we in the last time we were getting some 38 megabits per second for the previous case, right? Now let's see what we get for case 2. Yeah, so as you can see, we get at the receiver side, we get a throughput of 30 megabits per second. We've encountered the same issue with the client side, but as I said before also, if we check the checksum, it matches completely. So we completed our task of performing. But here you can notice here that the throughput is less than what we achieved in case 1. I'm giving you the same reason why we have that, because it's again the reason that I gave before, that the throughput capability is very low in comparison to what we were getting in the MT1500 case, even though we have an increased buffer size. So this is the TCP throughput that we are getting. I'll even show the bandwidth. just to compare. Yeah, so now it's 768 kilobytes, and we are performing with throughput of 30 megabits per second. There we were getting, I think we were getting around 5 megabits per second. Well, yeah, 5 megabytes, sorry, not bits per second. 5 megabytes, that's what we were getting in the transfer throughput. So this is the critical thinking section that we were, that the problem statement asks. So the value is lower in this case as compared to the case where we were running on an MTU 1500. Yeah, so now we do case 3, which is there was no packet loss in any of the networks, but the link speeds, there's a mismatch in the link speeds and the delay is 200 milliseconds, RTT. So that's why we set a delay of 100 milliseconds in EE0 and EE1, and the link speed as 80 megabits per second, but the client side remains the same. CQ disk, sure. Right, now what we will do now is run the same command, tracepath, just to check whether we are able to send jumbo frame. As you can see, we are able to, and we do the same thing the other way. 1.236, yeah. Sorry, I forgot about the IP address of the client. So this is the IP address of the server, and this is the IP address of the client. And now we run our script. Bash frftp client. Ping is this thing. We do the same way on the server side. 001. 001, because that's the MTU size that we set. And oops, let's send here. And run the same script, same thing. The only difference between case 3 and all the other cases is there's no packet loss, and there's a mismatch in the link speed. So as you can see, the files have been created. The datagrams are obviously less than what we were sending in the 1500 case, and let's see what the output is. So as you can see, we are getting 37 megabits per second. Same issue that we faced, but we can check the checksum, same as before. The checksum matches, so we do transfer the file 1 gigabits per second. 1 gigabyte file. Right. So it's the same reason, same throughput reason that I gave previous case. It's less than what we got in the 1500 case, slightly less. I think if I'm not wrong, it was around 40 Mbps, and now we're getting 37, which is more than the case 2 on the 901, but less than what we got in MTU 1500 interface. And that concludes all the 3 cases for the 2 interfaces, MTU 1500 and MTU 9001. Thanks.